In our last lesson on chemical bonds, we saw that sharing electrons is rarely an equal split. When one atom pulls harder, when it's more electronegative, the shared electron pair leans in its direction. We can measure that unequal pull. Because the pull has both a specific force and a direction, we draw it as an arrow pointing toward the stronger atom. We call this specific tug-of-war a polar bond. But most molecules have more than two atoms. If a molecule has multiple bonds, it has multiple arrows point at the same time. The question we have to answer is, where do all those arrows point when you combine them? The final sum of all these poles is called the dipole moment. It tells us the true electrical nature of the entire molecule. Let's look at this diagram of a water molecule. It sits in an angular geometry. Those non-bonding electron pairs push the shape into a V, and both hydrogen atoms have their electrons pulled inward toward the central oxygen. Because of that angle, the two arrows work together. They merge into a single downward pull. The molecule has a distinct positive side and a negative side, making it a polar molecule. Now look at carbon dioxide. The oxygen atoms still pull harder than the carbon, but CO2 has a perfectly flat, linear geometry. We have two identical forces pulling in exact opposite directions. It's a perfectly matched tug-of-war. The pulls cancel out to zero, leaving us with an apolar molecule. Having polar bonds inside a molecule does not guarantee the molecule itself is polar. If the geometric shape is perfectly symmetrical, the poles cancel. Let's test this with a 3D structure, carbon tetrachloride. We have one central carbon with 4 chlorines pulling outward in a tetrahedral geometry. Think about the shape. 4 distinct polar bonds, all pulling outward into space. Is the entire molecule polar or apolar? A tetrahedron is a highly symmetrical shape. Like 4 people pulling a rope toward the 4 corners of a square, the 3D vectors precisely cancel out to zero. The molecule is apolar. Because it is completely apolar, carbon tetrachloride was used for decades as a dry cleaning solvent. It could dissolve apolar grease and oil stains from delicate fabrics without needing a single drop of water. To understand a molecule's behavior, you have to look past its ingredients. 3-dimensional symmetry is the ultimate tiebreaker. This flowchart gives us a repeatable 2-step checklist for any small molecule. First question, does it actually have polar bonds? If the atoms pull with the same strength, you stop here. It's apolar. If it does have polar bonds, move to the second question. Does the geometric shape cancel those arrows? Let's run ammonia through the test. Yes, it has polar bonds, but it has a pyramidal geometry with an extra electron pair on top. The shape isn't perfectly symmetrical, the arrows don't cancel, and we get a polar molecule. Following these 2 questions in strict order eliminates the guesswork. It solves polarity for any small molecule you'll see on a test. We see this geometry at work every time we visit a gas station. Water is polar. Gasoline is apolar. They do not mix. Yet the ethanol we pump into our cars mixes easily with both. Here is how ethanol does it. One end of the molecule has an oxygen-hydrogen bond. This creates a polar tip that bonds seamlessly with water. The other end is a 2-carbon chain. This section is completely apolar, which allows it to interact directly with gasoline. Ethanol acts as a chemical translator. Its dual-nature geometry allows it to bridge 2 liquids that would otherwise instantly separate. Up to now, we've only seen electrons being pulled slightly to one side. Next time, we'll look at what happens when they are permanently stolen, and why rust on a gate and fire in a stove are exactly the same reaction.